And let me share my screen.
Is this
All
our
right.
last chapter?
Again,
Section? Is this our last section?
we're going to finish out 9.5 and do 9.6, and that'll be it. And 9.6 is just showing y'all how to use another formula. So 9.7. So I'm going to finish 9.6, and then we'll finish 9.7. So this is still doing the logarithmic equations. So I made it down to 14 because at 14 I wanted to show y'all a new property, and this is called the log base property. And this one says if you got two sides that equal, log A of B equals log A of C. So as long as you got two sides equal and the logs have the same base, then we know that B has to equal C. So it's about like that base exponent. When you rewrote them with the same exponents and the same base, we said that the exponents were equal. So same thing here. If you can write both sides with the same logs, then that means B has to equal C. So at number 14, we're going to have log base 4 of x plus 14 minus a log base 4 of x plus 6 is going to equal a log base 4 of x. So I'm going to utilize that log base property because I got logs on both sides of this equation. But the first thing we want to do to this on this left side is write the two logs as a single log. So I'm going to write this left side as a single log. So it's going to be a log base 4. Now, since these are being subtracted, I got to write them as a quotient. So we'll have the x plus 14 on top, and then the x plus 6 on the bottom. So remember, if they're being added, we write them as a product. If they're being subtracted, you write them as a quotient. And then that's going to equal the other side, which is a log base 4 of x. So now we got single logs on both sides. They both have the same base. So now we're going to utilize the log base property. Since these logs are equal, then we know that the x plus 14 over x plus 6 has to equal the right side of the x. So once you got the logs equal, this part will equal that part now. So an interesting little equation. I'm just going to put a 1 under the x to make it look like a fraction. And I'm going to cross multiply. And that's the easiest way to do these when you got one fraction equal to another. You take the top of one fraction times the bottom on the other side. So that'll be a 1 times the x plus 14. That's going to equal the other top times that bottom. So that'll be the x times the x plus 6. Okay, so I did top times the bottom, and then this top times that bottom. Now I'm going to distribute so that I get an x plus 14 on the left side when I distribute the 1. Right side will give me an x squared plus 6x. So I see the x squared term in here, which means it's going to end up being quadratic. So I need everything on one side equal to 0. So I'm going to subtract the x and the 14 from both sides. So I'm going to subtract the x and then the 14. So I get a 0 on the left side like I needed. And then I get an x squared Let's see, 6 minus 1 will leave me 5x's minus my 14. So at this point, we could use quadratic formula. A is 1, B is 5, and C would be a negative 14. Or you can factor it either way. It's going to give me two answers. It's going to give me a negative 7, whoops, and a positive 2. So remember, I need to check my answers, because if I put a negative 7 back in for this log right here, log base 4 of negative 7 would give me an error message. So I cannot keep that negative answer, and the only answer would be x equals 2. So you got to make sure you check those answers when you get them negatives, okay? All right, what's that, 15 now? All right, 15, we got a log base 2 of x plus 1 minus log 2 of x equals 2. So notice this one's got logs on the left side, but I do not have any logs on the right side where the 2 is. So I'm not going to be able to use that log base. So what happens when you cannot use the log base, we got to rewrite these as exponential. But remember, the first thing we want to do is rewrite those two logs as a single log. And y'all, once again, they're being subtracted, so it's going to look like division. So I got a log base 2, x plus 1 over x is going to equal 2. So all we did was rewrote the two logs as a single log, and they were being subtracted, so we wrote it as division. Now, since I don't have the logs on the right side, I'm going to rewrite as exponential. So I'm going to take my base, which is 2, raise it to the exponent, which is the 2, and 2 squared has to equal x plus 1 over x. Okay, so remember, the 2 is your base, this 2 is your exponent, and then that equals that result. So 2 squared, I'm going to turn that into, what, a 4? And y'all think I'm going to what? Put me a 1 under the 4 and cross multiply. So I take this 4 times the x, so that'll give me a 4x. That's going to equal to 1 times the x plus 1, which will just give me what? An x plus 1. All right, so let me subtract the x and get all the x's on one side. And notice the difference on this one, I didn't have no x squared term, so I didn't have to worry about using the quad and factoring. So I get 3x equals 1, and then y'all divide everybody by 3. And let's see, 1/3 I cannot do with nothing with. So 1/3, final answer. So they're not real bad. You just kind of sort of keep up with what type of equation are you solving when you get to that point on these, okay? All right, so 2 more for this section. Okay, how about this? The log 3 of x plus a log base 3 of x minus 1 is going to equal a log base 3 of 6. All right, so here we go. This one does have logs on both sides, so I'm going to try to get a log equal to a log on this one. So the first thing we got to do is rewrite the left side as a single log. This time they're being added, so I'm going to write this as a product. I got my log base 3 of x times x minus 1 is going to equal my log base 3 of 6. And that's the main thing you got to watch for on these. Are they being added or subtracted? So y'all, let me do one more thing. I'm actually going to multiply that x and that x minus 1 together. So I get a log base 3 of an x squared minus an x, all equal to my log base 3 of 6. All right, so now we do got logs on both sides, and the log bases match. So since my log bases match, I know that the x squared minus x has to equal the 6. So at this point, we do have a quadratic equation because of the x squared term. So I need to get everything on one side. So I'm going to subtract 6 from both sides. So I get an x squared minus x minus 6 equals 0. So on quad, you could do a is 1, b is -1, -6.
3 and -2.
3 and -2. So let's see, the 3's not bothering me, but notice when I put that -2 in for that x, log base 3 of a -2 would give me an error. So we cannot keep the -2 answer, and we only keep the 3.
So you cannot use the negative number at all.
Well, you want to check them. Anytime there's a single x up here like this, any negative would make it not real. But you got to watch out sometimes, because sometimes it might have like an x plus 7. And if I had an x plus 7, when I put a -2 in there, it would still be positive. So you just want to check and see when you put it in, does it make it negative or not, okay? But generally,
Okay.
the way we got ours set up, if you pretty much get a negative answer, you'll probably throw it out.
So does it matter which one you check it in?
No, I always check the single one, because if it's negative, it's going to make that negative no matter what, and it's going to be gone. Okay. But say that was like an x plus 5, x minus 1, then I would definitely really check them and see if it's keeping them negative or not. Okay. All right, let's see. The last one on this section has a log base 3 of an x plus 12 plus a log base 3 x minus 12 equals 4. And I tell you what they're doing here, they're just going back and forth between the ones where you can use the log base and then the ones where you got to rewrite them as exponential. So notice this one don't have a log on that right side, so I can't use the log equal a log. So this one I'll probably have to rewrite when we get to that point. But first thing, on the left side, we're going to rewrite as a single log. It's almost like that's like terms type stuff, you know. Got to get it out of the way. They're being added, so we'll rewrite this as a product. So log base 3 x plus 12 times x minus 12 will equal 4. Now, I'm going to FOIL this so that I can get it multiplied out. I'm gonna show y'all a shortcut when you got conjugate pairs like this, x plus 12, x minus 12. A shortcut would be multiply the first two together, the x times the x gets me an x squared. And then it's going to be minus the last two multiplied together. So let's see, 12 times 12 is what, 144? That's all going to equal positive 4. So these, you didn't have to FOIL the whole thing out, because what happens is the outer gives you negative 12x, the inner would give you a positive 12x, and those are going to cancel every time. All righty, now I've got a single log equal to my number. I'm going to rewrite as exponential. So my base is the 3. My exponent is the 4. And we know 3 to the 4th has to equal x squared minus 144. So let's see, my next step would be to figure out what 3 times 3 times 3 times 3 is. So that should give us what? 81 equal to x squared minus 144. So y'all notice we got the x squared term, so I'm going to get everything on one side equal to 0. So let's minus the 81. So I get 0 equals my x squared minus, I think that's what, 225?
Yep.
You want to use the quad. A is 1, B is 0 because there's no x, and C will be negative 225. That's going to give you two answers. It should give me what a, I'll get one a 15 and a
Negative 15.
15. So now, you see here I had an x plus 12, so let me check negative 15. If I put a negative 15 in for that x, negative 15 plus 12 would give me a negative 3, which means I cannot take my negative 15 answer. So that our only answer on that would be what? X is a positive 15. So if you notice on your homework, if you're getting negative answers, you're probably going to throw them out of there, okay? All right, so it all came down to one more little formula for y'all. And I don't guess my business people are here today, are they?
No.
Howdy, y'all. 9.7 is applications and models. But what we're going to mainly look at is what we call growth and decay. So these would be the ones that you can use like on the interest rate problems when you have continuous compounding. Okay, so I'm going to give you all a new formula. So this is for growth. So growth, we have P of t. So remember, t is my variable for time. It's going to equal P subscript O E to the K times T. So let me go through and tell you what we got. That P to the O there, that is my starting amount. So like if they say we invest $5,000 at blah, blah, blah interest for so many years, 5,000 would be my starting amount. E, we know what that is. That's the natural Euler's number. K is the growth rate. Or it could be the interest rate. Guess what T is? T is
Time.
always time. And then where I got the P of T, this gives me the amount at any time T in the account. Or in the population. You're using P's on this because a lot of times when you see exponential growth, it deals with the population. So this would be like your population in any year would depend on your initial population times E to the KT, where K is the growth rate and T is the time in years. Now, decay is the same thing pretty much. It'll be a PT equals PO E to the negative KT. So the only difference is decay is negative on the decay. Okay, so that's going to be your decay rate. And you'll use it when you see a decline in your numbers, okay? All right, so the last of these formulas I'm going to hit with is what we call the double time. It's the amount of time it takes for your investment to double. So double time will be a capital T So double time will actually equal the ln of 2 divided by RK. Now the thing about K is it must be in decimal form. Also, based on this double time formula, you could switch the K and the T around, and K would equal to ln of 2 over the double time. So I can find growth rates also if I knew what the double time was on them, okay? All right, so those are our formulas. We're about to start going on through these. So y'all got them listed, and I'm going to start with number 1. So in 2012.
Is it too late to drop out?
Oh, you don't, this ain't bad. Y'all get on up here. This is the last thing of the year. So look at this. In 2012, the population of a city was 5.38 million. Then it tells me the exponential growth rate was 3.85% per year. So that'll be the growth. So for A, they just want me to find the exponential growth function. So we're going to find the exponential growth function. So basically the equation you would use to find how much it's grown at any time t. So we know it's going to be P of t. So P of O, we want our starting amount. Well, the starting amount, the PO will be the 5.38 million. So I'm just going to write 5.38. We're going to assume that any answers are going to be in millions. All right, then we had our E in the formula. Then we had K, but K we got to play with for a second, because K is 3.85%. We need to turn that into a decimal by moving that left 2 places. So if I move left, I'm going to get a 0.0385. So we put that in for the K, 0.0385. And then we put our T for time. So what this tells me, if I know how many years, I can plug in for the T, and that'll tell me how many people are in the population. But y'all, that's all they wanted for that, was to come up with that equation and be done. Then it says, in 2018, the population is blank million. So what you got to do is figure out how much time is. So they're telling me 2018. I'm going to take the 2018 and subtract the starting amount, which was 2012. And let's see, 2018 minus 2012 means what? 6 years. So I'll use 6 for my T and figure out what we get. So we're finding P of 6 will be 5.38 E to the 0.0385 times 6. Y'all, so we just plug that in to see what we get. And let's see, they want us to round 1 decimal place. So 5.38. Since this E has exponents, I'm going to hit second LN and use that one. And then I got 0.0385 times 6 as my exponent. I hit enter and I'm getting 6.77. So that'll be what, about a 6.8? So that for my answer, in 2018, the population is 6.8 million. Now, you started with 5.38. If you got any number that was less than 5.38, I would redo it and check your math on that, okay? Because you're growing, so you can't be smaller. All right, let's see. Oh, I like this kind too. So check this out. The population will be 8 million, in about blank years. And then it says after 2012. So now we're not looking for the time or the amount after a certain years. What they want me to do is find what year will it be, or how many years after 2012 will it be 8 million. So 8 million would be the ending amount. So we're going to put 8 million equals my 5.38 E. K I know is 0.0385, but what I don't know this time is the T for the years. So we're actually going to solve this for that T. So the first thing you would do is divide both sides by that 5.38. Now, I'm not going to divide it yet. I'm going to leave it as an 8 over 5.38. That's going to cancel on that side, and I get an E to the 0.0385 T. Now, to bring that exponent down, we got to take ln of both sides.
Square root.
Ooh, do the ln, remember, because the ln brings those exponents down. So we will have the ln of 8 divided by 5.38 equals the ln of e to the 0.0385t. So now I'm going to do the left side. I'm going to do my ln 8 divided by 5.38, close parentheses. The reason I wait to divide is because if you divide before you do the ln, you're going to lose accuracy if you don't bring all them digits with you, okay? So if I divide after I take my ln, then I get a 0.3968. So 0.3968 will equal my 0.0385t. Because remember, the ln of e part equals 1. All right, y'all, did my last step. Take that 0.3968 and divide both sides by 0.0385. So let's divide by 0.0385. So I'm getting, what's that, about 10.3 years. So that one would be 10.3 years after 2012, which would be 2022 sometime. Now the last part of that, the doubling time is about blank years. So the doubling time is about blank years. So that's going to be the formula where I use the capital T equals the ln of 2 divided by the k. So on top, I'm going to have the ln of 2. Now my k I already made into a decimal form. That was what, 0.0385. So when we divide this out, we should get the amount of time it takes for that population to double. So let's see, we got ln of 2, close those parentheses, and then divide that by 0.0385. And that's going to equal, what am I getting, about 18.0? So that'll be 18.0 years. So y'all can do that if you wanted to find a doubling time to see how long it takes to double your money. If you know the interest rate you're getting charged, like 6%, you can divide ln 2 by 0.06. So let's see, ln 2 divided by 0.06. So if you had a 6% interest, you would double in about 11.5 years. That's pretty cool though, ain't it? Maybe. Alrighty, so for number 2, they're giving us a little chart to fill out. So the first column will be population. Then you're going to have the growth rate, which will be our K, and the doubling time, which will be our T. So you got the 3 columns. Down here we got country A and country B. Now for country A, I know the growth rate is 1.9% per year. And then I know the doubling time of country B was 46 years. So it's almost like you got 2 rows and 2 columns. We're looking for the doubling time for country A. and the growth rate for country B. So first, let me find this doubling time for country A. So here's country A. I know his doubling time, T, is going to equal to ln of 2 divided by his growth rate. But remember, that's 1.9%. I'm going to have to move that decimal twice to the left so that I get a 0.019. Hey, y'all, so then let's divide that. Well, what I got it, ln of 2, close parentheses, divided by 0.019. And that gives me 36.4. And they want me to round to the nearest year, so I'm going to round that down to a 36. So that's where I got my 36. That's my first answer. Now, I'm looking for the growth rate, and the growth rate I'm going to write as a percent. So remember, we said that for country B, well, K is going to equal ln of 2 divided by the doubling time. All right, we know the doubling time it took was 46 years. So we'll have the ln of 2 divided by 46. So you get a 0.015, but remember, we got to turn the decimal back into a percent by moving that decimal to the right 2 places. So I get a 1.5%. Now you just got to put into 1.5. They will have the little percent thingy there already. All right, so I'm going to try to knock out a few of these kind of problems today.
How many questions are on this section?
I'm going to student number 4, but they're like 6. And the last 2 are just one little part each. It's the first 4 you got to get through. So the first one was sort of like this, and so I'm going to do one where you got a decline in it. So I'm going to draw a little table here, okay? So it'll say year, and then it says percent of adults who are married. So I got 1960, 1980, 2000, 2010, and 2012. Then over here you got 68.2, 62.2, 54.3, 46.1, and then 43.5. So notice they're declining on this one, okay? So the first question, they want me to find K. So to find K, you're going to really work the formula in reverse. And you want to use your beginning and ending amounts for the K. So the ending amount was 43.5. So we're going to set 43.5 equals the beginning amount, which was 68.2. times E to the K. Now T, let's figure out how many years went by. So from 2012 to 1960. Oh, that's what, 52 years? So that my T will be 52. So what we got to do is solve for the K on this formula. So remember, the first thing I'm going to do is divide both sides by the 68.2. But remember, I'm not going to divide that left side yet, okay? I'm going to leave that 43.5 over 68.2. That's going to equal E to the K times 52. Now I'm going to take LNs of both sides. So the LN of 43.5 divided by the 68.2 will equal to LN of E to the K times 52. All right, so now that I got this, I'm going to work the left side. So let me do a LN of 43.5 divided by 68.2. So that's going to give me a negative 0.4497 equal to my K times 52. All right, then the last step, divide by 52. So log, let's see, what am I getting? Looks like a 0.0086 equal to my K, which is what I expected because it's a decline. My K should be negative. Now, when you put this answer in, this negative is always in the formula, so do not write the negative when you're writing down decay. Decay will be just a 0.0086. But the second part of this is to get the formula, so here we go. So they're using the M of T this time, but the same thing. M of T will equal my initial amount, which was 68.2, times E to the negative 0.0086 times T. So now that I know my K, I can find for any time T, I can see how much has my population decreased. Alrighty, so now let's see what they want. So for part B, they want to know percent of adults married in 2015 and 2018. So basically, I've got to use my formula for the 2015, then come back and use it for 2018. So for 2015, let me see how many years that'll be. So that'll be 55 years. So we'll do 2015 first. That was 55 years. So your formula will be M of 55, because it's 55 years, equals the initial amount, 68.2, E to the negative 0.0086 times 55. Now, what's nice about this one, I can punch everything in like it looks. And we should get our number of adults that are married in 2015. So 68.2 second ln to get to E, and then that's a negative 0.0086 times 55. Now, if you got the older calculators, when you do the ln, it's going to give you a parenthesis. Put everything into parentheses, then shut it. All right, let's see, what am I getting? I'm getting, it looks like 42.5. So that means in 2015, only 42% of Americans will be married. All right, let's check 2018. So 2018, what's that? 3 more years.
59.
So that'll be what, 58 years? So same formula, throw in a 58. Oh, and then what we say, 58. Alrighty, y'all, so 68.2 second ln, and then that's a negative 0.0086 times, what do we say, 58? And that's what, a 41.4. Which I would be happy doing this problem because it's declining, and both of my answers are declining from what they gave us in the beginning. All right, then the last part of this for C. In what year would a percent of adults married be 30%? So now we're looking for the years or the time. And they're saying, when will it be 30%? So 30% will be my ending amount. So 30%, that 30 will go into ending amount. The initial amount will still be the 68.2 E to the negative 0.0086 times T. So what this will give me is how many years. I'll add the years to the starting amount of 1960, and then that'll give me my actual year that this will happen. So since I'm solving it for the T, I'm going to start out by dividing by the 68.2. So I get 30 divided by 68.2 will equal E to the negative 0.0086 T. And then, like we've been doing, we're going to take the ln of both sides. All right, so let me divide that out and see what that'll give me. So ln 30 divided by 68.2 is going to give me a negative 0.8212 equal to my negative 0.0086 T. So at this point, divide both sides by the negative 0.0086. So let's see what that's going to give me. So divide by, what do we say, a negative 0.0086. Oh, and let's see, they want me to round to the nearest year, so I'm going to call that 95 for my T. But remember, I need to take 1960, add my 95 years to it. So I get what, a 5. So 2055 is what they were looking for, the year of that, okay? All right, so I think I can get through some of these short ones back here. So this will be like number 6. So there are currently 69 million cars. They decrease by 5.6% annually. How many years until they have 46 million cars? So this is not America they're talking about, because we don't decrease in cars. We would probably be increasing in cars. So we're looking for the time on this one. So the ending amount they were looking for was the 46 million. So the 46 will be my ending amount. That's going to equal my beginning amount, which was 69 million. E to the negative KT. Now, K I know because that's what, 5.6%. That would equal 0.056. So I'm going to put that in for my K. So that basically now all we're looking for is that T there. So remember, start out by dividing by the 69. And then I'm going to take the LN of both sides. So remember what that's going to do? That's going to give me a number on the left side. So let me see what the LN of 46 divided by 69 equals. So I'm getting what, a negative 0.4055 equal to my negative 0.056 T. And see what's neat about these is now you got a negative on both sides. When you divide by that negative 0.056, it's going to make my time positive like it needs to be. Oh, I'm getting 7.24, so they want me to round to the nearest years. So that would be 7 years. Well, hell, I guess I got time to do the one I skipped. So I skipped number 3, so we got time for it real quick. So for number 3, we're going to suppose 17,369 is invested at 6.6% per year, compounded continuously. So A, we're going to find the exponential growth function. And that just means find me the formula they're going to use. So remember, continuous compounding, use these formulas. If it's semi-annual, quarterly, stuff like that, then we use those equation with the 1 plus R divided by N stuff from the other day. All right, let's see. P of t is going to equal my initial amount, which was the 17,369 e to the k. So let's figure out, we got 6.6%. That's going to equal what, a 0.066. So that'll be my k. 0.066 times t. So if I know how many years have passed, I can find out what amount is available in my account. All right, so that was part A. Then part B, what is the balance after 1 year, 2 year, 5 years, and 10 years? So let's see, 1, 2, 5, and 10. All I'm going to do is use my formula, and in place of the t, put a 1, then in place of the t, put a 2, and so on. So my formula is 17,369. Second ln to get to e, 0.066 times 1. So the first one's giving me, looks like 18,554. We're going to round to the nearest cents. So that looks like a 03. So I'm going to go 18,554.03. Now for 2 years, I'm going to do the same formula and put a 2 in for my t. So 17,369, second ln, and then I have 0.066 times 2. When I hit that in there, I'm getting 19,819, and let's see, is that a 104? So that'll be what, a 0.91. Zeros and eights are hard for me to tell on these calculators. All right, so 5, same formula. Put a 5 in for the t. So 17,369. Second ln to get my e. 0.066 times 5. When I do that, I'm getting 24,159 and 73 cents. Now, the one thing you got to make sure, y'all, since we're investing our money, hopefully it better be going up every year. So after this 5 years, if I invested 17,000, I'm already up to 24,000 at 6.6%. So let's see what happens at 10. So the same formula, 17,369, second ln to get to e, and then it was 0.066 times 10. So it should be going up still. So let's see. Looks like what, 33,605, and that looks like 41. So after 10 years, you done made about $16,000. That ain't bad. All right, the last thing we're going to do on here. The doubling time is blank years. So we want to know, how long does it take for my $17,369 to double? I'm going to tell you, we're pretty close, because look at 10 years is at 33,000 already. 17 doubled is barely over, what, 34, 35,000? So we know it's going to be t to doubling time equals the ln of 2 over k, which is 0.066. All right, so here we go. ln of 2, close parentheses, and divide by 0.066. Now let's see, we're going to round to 1 decimal place. So I got what, a 10.50, so I'm going to round that to a 10.5. So in 10.5 years, you can double your money at 6.6% interest. Not too bad. Alrighty, so that's pretty much all of those. I think there's one little bitty one I didn't do. But it wouldn't be bad on y'all, so give y'all time to challenge yourselves, right? Y'all, guess what? That is college algebra completed.
Yeah.
There you go. So see, there ain't much left other than we'll review Wednesday for our test. And then I'll have that test open till Sunday night. Next Monday, we're gonna review for the final exam. And I think they're working on getting us a study guide online for y'all to play with. So we'll see how it goes. So let me see. Let me get one more down. That was.
Hey, Mr. Rathbun.
Huh?
I have a question for you because I was trying to figure it out last night.
Uh-huh.
My daughter does not have the cord that we need to transfer all the programs over to her calculator like you did ours.
Uh-huh.
Is there a website where I can go in and download all of those to her computer? Yeah, calculator. You might as well say computer, Shaterica. It's nothing but a handheld one.
I'm
It
trying to
does
think.
our
I don't
thinking
think
for us.
the ones I got are not like really online anywhere. So let me think.
She's got the cord that has the USB part to it, but it doesn't. It didn't come with the one that you can hook up from calculator to transfer them. And I don't know how I would do that.
I imagine you can buy one
You
on
either need
Amazon
this
for a few
one.
dollars.
Can you see that? She either needs this cord or the one most of y'all got nowadays is this cord.
Yeah, that's one I got on mine.
If you had one of them cords, I could tell you how to do her calculator. But it's got to be one of the.
Can you tell me the steps to do it? That way, if I can find one, I can do it and not have to bother you.
Oh, I don't mind you bothering me because it'd be easier to show you on here than to tell you. But watch me. Watch my. I'm going to bring up 2 calculators so you can see me real quick, okay?
Okay. Do you have a cord that has little prongs that will fit into here? On each one? I think so, yeah. Well, if you got it, let me get it so I could try to do that. He's going to show me how to do it real quick.
Oh,
It
how old is this
comes
girl?
with the new calculator.
How old is this child?
18.
18? Oh, okay. I didn't know you to bust out the
The
high
one that
school
has Miss Hanson.
teachers.
He has Miss Hanson.
Oh, okay.
No, my 14-year-old doesn't need it. He can do it in his head.
Uh-huh.
I've already watched a couple of your lecture videos that Miss Hanson posted so we can learn our math.
Why didn't you give me this last night, girl?
I didn't know. I did not have someone who needed.
All right, so plug them calculators up. 18-year-old, yeah, tell her she's probably going to have to owe me like $50 for this.
She can hear you. Let me see
45
if I can
for family discount.
Okay, hold on.
All right, so both them calculators are
the
on.
ones that were too big.
Huh?
She brought me the ones that were too big.
Oh, the USB?
No, the little adapter things.
Oh.
They're too big to go in that little bitty hole.
Oh,
No, not that I know of. I can't find any.
You don't have one?
No.
Well, crap.
well, hey, this is being recorded. Danielle, this is being recorded. So you can probably find one of them chords at somewhere here, I don't know. But this is the calculator. I got the programs in, going to the one that don't. So the first thing I do, the calculator that I'm wanting to put programs in, I'm going to
Okay.
hit second, and then the X to get the link. And I'm going to go highlight, receive, and enter. And it says it's waiting. Then I go to my calculator and hit second link. And I'm going to go to program and hit enter. And then you go through and highlight all the programs you want to put in. So I'll just go through, highlight all my programs. Once I've highlighted all the programs, I go to transmit on the top, hit enter, and then it's going to send them right in there. But see, this one already has them, so it's telling me, hey,
Okay.
that's it. Once you put them in, you're done. Okay?
Okay.
So it's not bad. It's just getting into them and being able to hook them up. So you can either use this one or you can use the one that I showed you a while ago with the little prong that goes in that part.
Okay.
So you gotta get one of them two chords.
Thank you.
Mm-hmm. All right, so y'all take about 10-minute breaks if y'all need a break, and then I'm gonna stop my share. And then I'm gonna quit